introduce a new light curve analysis program called PYOTE. PYOTE stands for Python Occultation Timing Extractor. It's been written by Bob Anderson, the same person who wrote PYOTE. He lives in Lake Oswego, Oregon. And we can move to the next slide. I'm sorry that Bob isn't able to do the presentation today. He's currently traveling in Europe and is inaccessible. So he asked me to do this presentation for him. I ran these slides past him, and so this is with his approval. Okay, so PYOTE is a standalone program for the analysis of occultation timing light curves. So in that regard, it's going to be similar to Ocular, if you used Ocular, or similar to PYOTE. It's a little different from PYOTE in that for PYOTE to work, you have to install all of Occult 4, and with PYOTE, you only have to install PYOTE. It's written in Python code, and that allows a simplified graphic user interface. It has a simplified installation over PYOTE, and it allows continually updating remotely via the Python repository. It's designed with all the same mathematical algorithms that are used in PYOTE, so it has the same accuracy, does everything exactly the same mathematically, so it's a mathematically equivalent to PYOTE. Compared to PYOTE, though, PYOTE is greatly simplified for ease of use, and I'll demonstrate that in a little bit. It can be installed in any operating system that supports Python code, and so far has been tested and run on both Mac and Windows operating systems. Next slide. The PYOTE uses a maximum likelihood estimation technique to determine the best fit of the model light curves, which are square waves, to the actual physical light curve. And so the physically realistic square wave models are fit to the light curves. Subframe timing is included, but only if an Akaike information criterion calculation indicates that subframe timing is justified. If subframe timing is not justified, meaning that the light curve is too noisy, then full frame timing is used. And then I mentioned earlier, PYOTE uses a statistically rigorous error bar calculation to properly characterize the uncertainty in the DNR time estimates and the error bars. And it uses correlated noise that is caused by atmospheric scintillation. It's very important because most Monte Carlo simulations have to use noise that is based on, that is Gaussian based. And Gaussian noise is valid, except that atmospheric scintillation causes noise that is also Gaussian and correlated. That means that blocks of data can fluctuate up and down based on the scintillation bubbles. And PYOTE and PYOTE both take that into account in the calculation of error bars. Next slide. So I mentioned after the question in the other presentation that occultation error bars are non-parametric. They don't fit any known statistical distribution, and we've checked all of them that we could find. Normal statistical relationships from Gaussian distributions like 1 sigma and 2 sigma don't apply and cannot be used. Um, so that's why error bars are created through Monte Carlo simulations, and then the error bars have to be calculated at the desired confidence levels. PYOTE is producing error bars at the 0.6827, 0.95, and 0.9973. And those confidence intervals are associated with, if you had a Gaussian if you had a Gaussian distribution, those would be the 1 sigma, 2 sigma, and 3 sigma equivalent levels. Next slide. Okay, so how do you get this thing to work on your system? PYOTE requires the installation of Anaconda 3 and Python on your computer. So it's kind of like, you know, if you want to use a Cult Watcher or a Cult 4, you have to have Net Framework on your computer. So that's what this is. Once you install Anaconda 3 and Python, then you're pretty much good to go. After that, PYOTE is self-installing off of the PYPL package repository. So we prepared a PDF file as a user guide to install Python, and we prepared those for both Mac and Windows operating systems. I'm providing the link here on this slide, and there's also a link on Brad's North American and worldwide websites. So you can get the PDF files on how to install PYOTE from Brad's website. And once you get PYOTE installed, then as you open PYOTE each time, alerts are provided if there's a future update, and that update can be automatically installed from the Python package repository, which is pretty handy. Okay, next slide. So some special features that Bob has provided. He has tips and instructions that are provided in pop-up text boxes when the cursor is hovered over the menu item, and that's something that I recommend you look at each of these tips and instructions. The light curve is tested for timestamp continuity, so if you have a VTI timestamp in your light curve, you use iMovie or Tangra, if there's a VTI timestamp on your video, it will transfer those timestamps into your CSV file. PYOTE will check those for continuity and see if they are valid. It supports both Tangra and iMovie CSV files. Once it gets the light curves, if you've got more than one star in your light curve, it can normalize your primary light curve to the secondary star light curve, which is handy if you have clouds or other atmospheric things that affect the data. It has a handy little start over button, so if you make a mistake or do something up, you just press the button and start over from the original light curve, which is handy. And the best feature that I think it has is that it creates a continuous log file. So every step that you do in the analysis of the light curve is recorded, and even if you start over, that start over is recorded, and then at the end you get your summary reports are all appended to the same log file. So if somebody's doing an analysis and they're having trouble, they could send me or Brad or somebody else the log file. We can look through that file see what you did and then resolve what the problem is. We found that to be very handy. Next slide. Okay, camera delay corrections are a difficult thing to deal with because there's so many cameras and it just gets to be very confusing. Bob didn't want to deal with that, so to keep PYOTE as simple as possible and not have a bunch of overhead maintenance for when cameras are added, he did not incorporate camera delay corrections into the PYOTE output disappearance and reappearance times. So when you get PYOTE disappearance and reappearance times, the results have to be corrected for camera delay. And you might say, well, that's going to be a mess. Well, in order to facilitate that, we created a new Excel form, that the same form that's included in Occult Watcher. And all you have to do is input the raw PYOTE disappearance and reappearance times into the form. Make sure that you have the right camera and the settings checked. And the form will automatically correct those results. And Brad says maybe the release will be in Occult Watcher soon. We hope so. Okay, and that form is available on Brad's website. I provided a link here on this slide as well. Next slide. So I'm going to do a demonstration, but I'll do that at the end of the presentation. So let's do the next slide. So some future development. So PYOTE is, it's brand new. It's a work in progress. Future updates will be automatically provided as Bob continues the development. So one anticipated future development that we've talked about is that after the person has processed the light curve, that sometimes you have to block integrate the data points. You might normalize it. You might trim out some awkward looking or bad sections due to clouds or something. Once you get a finished light curve, the idea is to output that to the IOTA Visier database like Dave Harold is currently doing with IOTA. And so that we're planning to work on. And as you use PYOTE, if you have any suggestions for changes or improvements, you can submit those to Bob Anderson at his email address, and that's included in a little PDF pop-up that he provides on an info button. Next slide. I think this is the last slide. So I'd like to thank Bob Anderson for putting in the effort to create PYOTE. I'd like to thank my IOTA RO volunteer group members who have been beta testing PYOTE for us, in particular Ted Blank and Greg Lyzinga, who came up with some good catches on errors that were in the code. And Brad, who has been supporting us all along the way, and was the recipient of the Dabble Award. So thanks, Brad. Okay, so if you can relinquish the presentation to me, then I can share my desktop. And if somebody can tell me if you can see my desktop, I appreciate that. yet, it says. Oh, I gotta press start sharing. Okay, that helps. And I'm gonna do full screen share, so you'll see my entire screen. Okay, so now you should be able to see my desktop. Is that correct? Alright, so I'm going to start by double-clicking on a little icon that we create that's got a little code in it. And the first thing you see is an Anaconda window that pops up. I want you to see this because when you first start PYOTE, it goes out to this repository, checks for a new program, and the screen just sits here and sits here for a while. And people will say, well, wait a minute, what's going on? It's not working, and then they click some buttons and then they mess it up. So the main idea is while the Anaconda screen is up, you just be patient and wait. Now if you have a faster computer and faster internet than I do, it might go quicker. But the end result is the PYOTE start screen, which starts like this. It has a window where the light curve occurs. It has a panel with instructions. If I hover over a button, a pop-up appears. I won't get into all the pop-ups, and I'm going to read a light curve. And I'm going to go to conference presentations. Okay, so this one will be a good Okay. Okay, so this is a light curve with 2 stars in it. There's a toggle here. If there's more than one back or secondary star, you can toggle and it would show those 2 light curves superimposed. The green would be the secondary star, the blue is the target star. And I can toggle the secondary star on or off. Okay, I'll leave it off so you can see. When we send out a light curve, we're going to tell people whether or not the data has been block integrated. But if you zoom in, you can take a look at the light curve and see if the data points are correlated to each other, meaning that maybe they were using integration and didn't tell us. But on this particular light curve, it looks like pretty random noise. So if after zooming, if I right click, I can unzoom and get my light curve back. And I'm going to do a quick analysis, so I have to analyze baseline noise. To do that, I click on a point left of the event, 2 points, and highlight all that data in between. I press Analyze Baseline Noise. I go to the right side, click on 2 more points, so I get all of that data, Analyze Baseline Noise. Then I'm going to analyze the event noise, so I click on 2 points in the event bottom. Oh, that one's down there. Analyze event noise. Once I've got my noise analyzed, I mark the D region with 2 data points. Compress mark the D region. I want to mark the R region. Press 2 data points around the R and mark the R region, and now I show those regions are highlighted. Don't have to be terribly precise. And then I press locate DNR. It says I'm going to get a lot of candidate solutions. Do you want to continue? I say okay. It's fairly quick. And I get a square wave solution to the light curve. All I have to do now is press calculate error bars. And I get an error bar solution. And my report is appended to my log file. And down here I have a running log file of every operation that I just did. All of my error bars are documented. My timestamp validity check is documented. So my log file is produced here, and I have all of that captured. I'm really done. So in my log file, I have a D time, I have an R time, I have a duration, and with my D and R times, I have error bars at the 0.68, 0.95, and 0.9973 confidence levels. That's all the data we need to supply for our report in the Excel form that we produce. Now that's one thing that I want to show you, and then another thing is I want to show you how it works when you want to normalize, and sometimes you have light curves that are odd looking. Here you have a secondary star which it's got a clearly a curved light curve to it, and the primary seems to follow that well. So we can correct the primary using the secondary, and we do that by just smoothing the secondary, and I do that by just pressing smooth secondary, and I get a nice smooth curve to that. And then I need to pick a point around which we're going to normalize. I usually pick something close to the event, so I'm normalizing close to the event. Press normalize around secondary point. I'll get rid of the show secondary star, and you see that the light curve has been normalized fairly well. And we could clean that up by trimming too if we wanted to get rid of the outside edges that didn't get normalized quite as well. Now I could go ahead and do a analysis of that like I showed you. I won't do that because we don't have enough time. And I wanted to show you one other thing, and that is the timestamp error marking. So this is a file I received from an esteemed observer whose name is Ted Blank, and I don't know what he was doing on his computer at the time. Oh, I think he told me he was trying to run a GPS device at the same time as he was trying to capture video, and he ended up with lots of dropped frames. I can take that. And you can see that between any two data points, if the timestamp between these two data points does not agree with an increment of a NTSC rate or PAL rate, whatever the appropriate rate is, it puts a red line in there. And so Ted had a lot of drop frames. Now the nice thing is about PYOTE is it's not, it doesn't care too much about how many drop frames you have. What it does is it tries to find an event, D or R, and then it counts the number of frames between the D and the R points, and then it checks the timestamps for the frame at the D and the R times. If everything agrees, it goes on and says you've got good data. So with this particular file, believe it or not, all of the analysis of the disappearance and reappearance for this file checked out with no timestamp errors. Alright. So that's what I wanted to show you. I'm going to stop sharing and I will accept